This is the second video for section 8.2, area of a surface of revolution, and in this video we're actually going to find the area of a surface of revolution. So we're going to evaluate surface area integrals, and this is a very example-driven question video, so we're going to be doing a handful of examples that illustrate the general techniques, but the idea then is there are really few nuances here that we need to worry about compared to what we did in chapter 6 with the solids of revolution, because here we're not going to generally be concerned with rotating about different axes other than the x-axis and the y-axis. So this first standard example, our task is to find the area of the surface generated by rotating y equals cosine of 1/2 x for x ranging between 0 and pi about the x-axis. So what that looks like, I have the picture drawn already. Saved us all some time and grief by drawing this before they started the video. But roughly then, we have this curve, the cosine of 1/2 x from 0 to pi. You'll notice that it's a constantly decreasing function over that interval. And then rotated about the x-axis, we get this surface that looks kind of like a cone. So if we want to find the area, we want to identify really two main pieces here. So first, what is the ds, right? So the infinitesimal arc length. And what is the full integrand of this function? So I'm going to write this as s equals the integral from 0 to pi of 2 pi f of x ds. The ds part, of course, that is going to be equal to the square root of 1 plus f prime of x squared times dx, okay? And the ds will have different meanings depending on whether we're working with integrating with respect to x or with respect to y. So just be careful that this is an overloaded definition here. So in this case, right, so we have f of x is our cosine of 1/2 x, which means f prime of x is going to be negative 1/2 sine of 1/2 x. So putting this into our ds becomes the square root of 1 plus, and then this expression is going to be squared. That's going to make 1/4 sine squared 1/2 x dx. Okay, so this is our infinitesimal arc length piece, and that's what we're going to rotate about the x-axis. Now, we'll plug this into the rest of the surface area calculation. So the integral from 0 to pi of 2 pi times f of x, which is cosine of 1/2 x, times the square root of 1 plus 1/4 sine squared of 1/2 x, and then put that all under the square root dx. Okay, this looks nasty. Don't worry though. What can we do here to simplify this? For instance, I think we can perform a simple substitution, keeping in mind that if we let this be u, not squared, but just the sine part, then our du is 1/2 cosine of 1/2 x, and that is already present here. This is part of the u. So that's going to be helpful. So we're going to perform that substitution first. So s equals the integral from, I'm gonna put in those limits of integration in a second. For now, I have 2 pi times 2, and I'm putting a 2 because that's part of the du, right? There's a missing 1/2 term, so really it's 2 du times the square root of 1 plus 1/4 u squared. I lumped in the dx from this side, so the du really was this plus a missing factor of 1/2, right? So that's what we accounted for there. And then, of course, what do the limits of integration become? So u of 0 is sine of 1/2 times 0, which is 0. And then u of pi is sine of pi over 2, which we know is 1. So these are our limits of integration. That's where it comes from. And now we just rewrite this in a way that's a little nicer to work with. So integral from 0 to 1 of 4 pi integral of 1 plus 1/4 u squared du. And there are a couple of different ways of working with this. So first, perhaps we can pull out a 1/4 from inside the square root. So if we pull out the 1/4, that becomes a 4 pi times 1/2 times the square root of, you guessed it, 4 plus u squared du. Integral from 0 to 1. And that we can work with because now we can perform a trigonometric substitution, right? So we know that whenever we have something of the form a squared plus x squared, in this case a squared plus u squared, we can let u equal tangent of, or 2 tangent theta, which leaves du equals 2 secant squared theta d theta. And then u of 0 is 2 tangent of 0, which is 0. And u of 1 is 2, we're performing the opposite operation, so it should be 1/2 tan inverse of 0. If you hear me pause abruptly or for like weird reasons, it's because it's the allergies. But that's still 0. U of 1, we're performing the inverse operation again. Am I doing this right? Not u of, sorry. Theta. Because we're transforming from u to theta. So then plugging in 1/2 tan inverse of 1. That's pi over 4. So 1/2 times pi over 4 is pi over 8. Okay. Then all this becomes the integral from 0 to pi over 8 of 2 pi times the part inside the square root becomes secant squared, so that's going to be times secant theta times 2 secant squared theta d theta. So pulling out of 4 pi, get the integral from 0 to pi over 8 of secant cubed theta d theta. At this point, because we've seen this one before, and we don't need to rehash, all the excruciating details of working with something like this, we're just going to go ahead and use the formula from the table of integrals for trigonometric forms. I have it right in front of me from the table that's provided in the textbook. So secant cubed of theta integrated is going to yield 1/2 secant theta tangent theta plus 1/2 natural log absolute value of secant theta plus tangent theta evaluated from 0 to pi over 8. And this is nasty because of all the different, operations that we're going to have to perform here, including, because of the 1/2 that we had to perform. Oh, I'm sorry. Yeah, I messed up here when I transformed the limits. Wrong inverse operation. It is tan inverse of 0 over 2, still 0. Tan inverse of 1 over 2. So what gives you an inverse tangent of 1/2? What does give you that? We'll leave that in there for now. But that's a different answer. So we're evaluating at two different angles. The 0 one, that shouldn't have changed. But we're evaluating a tan inverse of 1/2. Okay, so that makes more sense. All right, and then at this point, right, so you'd have to plug these in. So, 4 pi, 1/2 secant of tan inverse of 1/2. Tan times tan inverse, or tan of tan inverse. Those are inverse functions of each other, so those just give us 1/2. Plus natural log of secant of tangent inverse of 1/2. And then I ran out of room here, but I'm going to go ahead and power through anyway. Plus tan of tan inverse is 1/2 in the absolute value bars. So that closes off the absolute value bars. And that first and that first evaluation, minus 4 pi times tan of 0, 0. So the first term becomes 0. And then 1/2 ln of secant of 0 is 1. So 1/2 ln of 1 plus 0, which is 0. So ln of 1, which is also 0. So that also goes away. And so really the only thing left here to do is just try to figure out what secant of tan inverse is, which is it's an identity that we can find pretty easily. It's not a huge deal. And in fact, in some cases, we're even justified in leaving it in this form. So that really is the answer. We could simplify a little bit further, but that is the answer to this example, which is a real number, right? Okay, so now let's do another example. And in this example, we're going to now find the surface area for an example in which we're integrating with respect to y instead. So we're going to set up that operation here. So find the area of the surface generated by y equals 1/3 x to the 3/2 for x between 0 and 12 about the y-axis. So about the y-axis, we need to modify our formula here just a bit. So in this case, our surface area calculation, we're going to need limits of integration for y And our integrand depends on y again. Sorry, not y. We're rotating about the y-axis, so again, we're going to need g of y times 1, the square root of 1 plus g prime of y squared times dy. And of course, this piece right here is the same as ds, except with respect to y, okay? All right, sorry, I just got confused there for a second. But this is a rotation about the y-axis, okay? And for this specific example that we're looking at, it's going to look something like this. And that 3/2 power means it kind of looks like this, roughly. Okay, so this is from 0 to 12 in the x direction, okay? And so it's going to hit some y value, and then we're going to stop at that point, okay? So this is the curve that we're, this is the curve that we're generating a curve out of. And so when we rotate it, it's going to look something like this. And so we're interested in a band based on an infinite